Okay, just going straight on. Now L, that was the position where of the second occurrence in the sequence of states the machine goes through of the repeated state. Okay, and that can occur either at the very end, I guess, or before the very end. You know, of the end meaning the last input symbol. So L would be less or equal to P plus 1. Now P plus 1 is less or equal to N plus 1. N is the number of symbols in your input string. So you play around with the P's and the N's and convince yourself, get familiar with the details. There are lots of nitty-gritty details in this proof. And you probably notice, the level of abstraction and the number of details and so forth. The level of reasoning is, it's getting up. I'd say this is probably first-year master's level now. I've been warning you all the way through pretty well that this will be happening. All right. Okay. So we can now split up the input string with its n, that it had n input symbols in the string, okay, from S1 to Sn. Okay, so now J, if you remember, that was the position in the sequence. No, wait a minute. What is J? Oh gosh, what is J? That's so Rj and Rl. Rj is, I guess, the position in the sequence of states where you have your first repeat state, and Rl is the position of your second repeat state. I assume that. Okay. So you split up your string, your S, which is X, Y, Z, into these three substrings. Okay, and this substring, this sequence of input symbols, that sequence of input symbols will take your machine from R1 to Rj. Okay, convince yourself of that. And then this sequence of input symbols will take you from Rj back to Rj, right? Because you got to repeat. Okay, and then this substring, if you like, this sequence of input symbols in your substring Z, that will take you from state Rj to Rn plus 1. What happened to L? Not mentioned. Oh, it's here. Here. Right. Okay. So X will take you from R1 to Rj. Y will take you from Rj back to Rj. And Z will take you from Rj to the accept state, right? And if you then pump your string S, then you just keep looping around. This multiple copies of Y you'll just keep looping. The machine will go through from state Rj back to Rj as many times as there is I. Okay, so this pumped string will be accepted. Okay, now all right. So that's condition 1 satisfied. Right now, J is not equal to L because L occurs further on, like at least one input symbol further than where J occurs. So J is not equal to L. So therefore, the size of the input string y must be positive. Okay? So convince yourself of that. That's what Sipser claims. All right? And from here, we've got L's less or equal to p plus 1. And again, Sipser just throws this at you. So again, I ask you to do this for homework. The size of the combined concatenated substring xy, the length of this substring xy, is less or equal to p. So convince yourselves that that's true. I ask you to do that to do that from homework for homework. Where does this come from? Let's just see off the top of my head. Obviously, the length of xy will be less or equal to the length of xyz, right? That might help you. What else do you know? You know that the length of xyz is n. You have inequalities between n and p, stuff like that. Okay, hopefully. With that kind of reasoning, those clues, hopefully that'll allow you to prove this thing, right? Because j is not equal to L, Sipser claims, therefore the length of this substring y is positive. Okay, that's condition 2 satisfied, right? And this here, that is condition 3. So you've shown now all 3 conditions have been satisfied by the pumped string, by this. Right? So you've now proved the pumping lemma. All 3 conditions have been satisfied. So let me just reiterate the pumping lemma again. This might help. Assume a language A is regular, right? Therefore, there is an integer, positive integer p, called the pumping length, and so then all strings of the language, call them S, of those strings, those that have a length greater or equal to the pumping length, little p, all those strings that are sufficiently long, they can be pumped. Right? That's what the lemma is saying. They can all, as long as the length is appropriate for a given p, pumping length, they can all be pumped. And what does pumping mean? It means that you can split up that string S into 3 parts, contiguous parts, x, y, z, such that 3 conditions. X, y to the I, z, belongs to the language. I is a non-negative integer. Second condition is the length of y is positive, not 0, it's positive. And the third condition is the length of xy is less or equal to p. This, and this belongs to the language. The pumped string S belongs to the language. Okay, so that's the pumping lemma. All right, now the question is, now how do you use the pumping lemma to show that a language B is not regular? Now, I actually talked quite a bit about that in the first session, so I won't go into this in too much detail, and just a bit quick refreshment. So you use it. You use the pumping lemma in a proof by contradiction. So you're trying to show that a language B is not regular. Okay? In other words, there is no machine that recognizes the language, because a regular language, by definition, remember, is a language that can be recognized by a machine, by a DFA, a deterministic finite automaton. Right? So you'll use the pumping lemma in a proof by contradiction. So you assume the opposite of what you're trying to prove. Right? You're trying to prove that B is non-regular. So the opposite of that is that B is non-regular. In other words, it's regular. So you assume it's regular. Now, if it is regular, therefore the pumping lemma applies, right? And that means that all strings, whose length greater or equal to some little p, pumping length, all those strings are pumpable.